In this module, we will look at transients on transmission lines. In the earlier modules on transmission lines, we considered sinusoidal excitation, that is we took a sinusoidal voltage source and of a particular frequency or equivalently a given wavelength, connected that to a transmission line circuit that could have loads, that could have different lengths, different characteristic impedance, all these things we saw. But we never really, although we know that the voltages on the transmission lines and other parts of the circuit were actually varying with time, but this time variation was all in the form of a sine or a cosine wave, right. So it was a sinusoidal waveform. There was no explicit requirement for us to mention anything about time because the waveforms were all going to be sinusoidal. The transmission line circuits that we analyzed so far were all linear, and all the circuits that all the waveforms that we had were all sinusoidal waveforms. Therefore, there was no requirement for us to explicitly mention the time dependent nature of voltages and currents. Okay. But in this module, we are not going to do a steady state analysis. So the analysis that we did so far was called a steady state, which means that the voltage sources were assumed to be connected for a long time, so that all the initial effects of connection, the moment you connect, there is some initial charge, initial charging of the transmission line, initial current flowing, initial voltages changing, all those initial things have died down, all those things have been done, and now the circuits have reached their steady state. That is what the analysis so far we have done. However, in many cases we are actually interested in those transients, that is, we are interested what happens when you take a transmission line and then connect it to between say two driver and a load, and if the driver voltage waveform is changing with respect to time, then how would the transmission line respond in time domain to this changing voltages. This is something that you would see quite often when you are looking at high speed digital designs. Okay. Consider a typical high speed IC which will have multiple things would be there, but this is the simplest thing which I would like to discuss. You have a CMOS inverter, okay, formed from some MOSFETs and other things. You have another CMOS inverter, okay. One CMOS inverter is driving another CMOS inverter, okay. It may be intentional or it may be unintentional, but one is driving the other. It need not be a CMOS inverter itself. It could be a capacitor, it could be a resistor, it could be something else that would be driving. But the point I want to highlight is that the signals that are going through this particular circuit are not the sinusoidal ones. They are in fact what are called as digital signals or digital waveforms. How would these digital waveforms look? Well, these digital waveforms, if you see, are what we call as the switching waveforms. Sometimes in the older literature they would actually be going from V high to V low, right. So in the case of a TTL circuit, these high and lows have a certain values, and in case of CMOS there is different values for V high and V low. Regardless of all that, there would be this switching, right. So if for example this can be considered to obtain a clock, then this output should actually continuously be switching compared to the input. Okay, so there's actually one more inverter is required, but that's another point. I have written something over here as an interconnect. On a high speed IC, the leads that connect one component to another component acts as a transmission line. Even though you don't want it to act like a transmission line, it does act like a transmission line because the distances involved are small, but the frequencies involved or the wavelengths involved are also small. So wavelength is small, frequency is high, and even a small piece of wire or a contact, this one would act like a transmission line. Okay, so it's just a copper thing which would act like a transmission line at almost all high speed digital circuits. Okay, of course all in the analog circuits as well. So on these circuits or on these interconnects, you have at the source side signals which are switching from high to low, and they are to be transported across to the second CMOS inverter which is acting like the load in order for this one to be allowed to switch. Okay, of course in practice you don't get a change from low to high in 0 time. What you see is much more milder versions, so you will actually see something like this, right. So you would see with a certain rise time and a certain fall time, these are the type of signals that you are going to see. Okay, these are much more practical, but nevertheless for this simple analysis we will assume that the signals on the interconnects obtained at the output of one component which we call as the source and to be transported to the load are switching like this. Okay, we will initially not consider the pulse excitation. We will assume initially that the transmission line or this source guy was not having any voltage initially at some t equal to 0, then arbitrarily it has actually changed its value. Okay, there is a step waveform that is launched on the transmission line. Now it's understandable, right? So you understand how the transmission line would respond to a step, and since pulse can be considered as one positive step and another negative step applied after the pulse period, right? So you have a negative going step. So if I know how the transmission line behaves for this step voltage, I know how it behaves for this one as well. So I can actually use superposition to simply understand how the transmission line would respond to a pulse. Okay. So this is the step waveform that we have launched at the input of the transmission line. Now from this somewhat realistic kind of a behavior, we are going to an idealized kind of a behavior. We will consider that there is a transmission line and then there is a load. Okay, this load is that CMOS load that we were characterizing. We will assume that this load is real. Okay, for this analysis we will assume that the load is real. So ZL is actually some RL. Okay, the transmission line is also lossless, having real characteristic impedance R0, has a certain length L. Okay, and we will also put down Z equal to L as the load point. Okay, and Z equal to 0 as the source point. Okay, so here let us assume that you have Rs, which is the source resistance, internal resistance of the source, and then the source itself is a step waveform having an amplitude of V0. Of course there is actually a switch which we will imagine connects this, the switch actually has to connect after Rs. So there is Rs over here and then there is a switch. Okay, so the switch is initially not connected, thereafter at time t equal to 0 the waveform is switched and then the circuit is complete. Okay, this is exactly what we have discussed earlier, but now I have replaced this CMOS driver by a voltage source and its internal impedance Rs, and I have replaced this load CMOS gate by this load RL. The interconnect is represented by a lossless transmission line having a characteristic impedance of R0. Okay, so this is our prototype circuit for analysis of transients on the transmission line. Okay, now before t equal to 0 there is nothing happening, so the voltage across the load is 0, but at t equal to 0 when we connect the load, when we connect the source to the transmission line, what would happen? We know that voltages on the transmission line are functions of both Z and T, right? In fact, for a forward propagating wave, the voltage would be something like V plus of T minus Z by V, and for a backward propagating or for the reflected voltage, it is V minus T plus Z by V. Therefore, the total voltage on the transmission line, let us call this as V line, will be sum of forward and backward voltages. Okay, what is this V here? V is the phase velocity. Let us not get into the reason why this is called as phase velocity and whether this is the same as the one that we defined earlier. We will defer all those discussions to some time later. What we want to show is that this V is related to L. Okay, because the delay of the transmission line is given by L by V. Okay, V can itself be written as C by square root epsilon R. So if the transmission line is filled with insulating material that is not air, then you have to calculate what is the velocity of light on the transmission line, and that would be C by square root epsilon R. So the basic idea here happens here, you know, like imagine that there is a length here. If something happens over at the source end, it will take Td time for this effect to be seen at the load side, right? So something happens L distance away, then it will take some time L by V in order to be observed at the load point. Okay, so this is the basic relationship between delay on the transmission line, length of the transmission line, and velocity of wave propagation or pulse propagation. Okay, so I hope this part is all right. Okay, we can similarly find out what is the, since the line voltages have to be continuous, right? So there is line voltage that is coming in here. This voltage must exactly be equal to the voltage at the source side. This must be equal to the voltage at the load side, right? So at the source side, what is the voltage on the transmission line? Source occurs at Z equal to 0. Okay, so the source voltage is basically given by V plus of T for all T such that this is less than L by V. Actually it would be up to 2L by V, but let's not go there out again. So at the source side, until for the time delay, the source voltage will be equal to only V plus of t. This would only be the forward voltage, there is nothing changing out there. At the load side, what would be the voltage? The load voltage will actually be at Z equal to L, and the load voltage is given by V plus of t minus L by V, which is precisely this voltage V plus of t that has been delayed by L by V. So if you were to plot this as a function of time, then this would be V plus of t. So let's assume that this is V plus of t. Then what would be V plus of t minus LB? V plus of t minus LB will be starting at a time L by V, okay, and then it would essentially be the same thing. So although I have shown this to be two different amplitudes, this amplitude exactly is the same thing. So this is V plus of t minus LB, which is simply a delayed version of your signal V plus of t, okay. So this is your V plus of t. But this is not the only way. The moment you have some voltage arriving, and if RL is not equal to R0, there will be reflections developed at the load, correct. So these reflections which will develop will create a negative travelling wave, right. So wave which is going towards the source. What is that voltage? That is some V minus, but it is supposed to be flowing in the backward direction. Therefore it is V minus of t plus LV, but this has to start only after t is greater than L by V. That is, only after you have received some voltage can the reflected voltage start to appear, okay. So the load voltage is V plus of t minus L by V plus V minus of t plus L by V. What would be the current total at the load? Current will be I of t Z equal to L given by Y0, which is the admittance of the transmission line, 1 by R0, at times V plus t minus L by V minus V minus t plus L by V, right. So we will also write down this one in a slightly different way. Since this is the first time we are seeing some reflection, so we can actually write this as V1 minus, nothing has changed in terms of anything. So all that we have done here is to remind ourselves that this V1 minus actually is the voltage that is developed in response to this V plus that arrived at time L by V. And for the time from L by V all the way up to say 3L by V, these things will be quiet at the load side, which means to say that there are no more reflections that are being generated, okay. So this is the current is given by Y0 into this thing, which is the forward going voltage plus negative travelling reflected voltage divided by Z0, that is Z0 is 1 by R0 or equal to Y0, okay. If you now look at the line voltage at Z equal to L and look at the current on the line, the ratio of these two must give you the load impedance ZL, which is equal to RL, and you can actually do this substitution, and what you will see is that RL is equal to R0 into 1 plus V1 minus t plus L by V divided by V plus t minus L by V divided by 1 minus, right, V1 minus t plus L by V divided by V plus t minus L by V. If you look at this equation, you will see something that is very similar. This is the ratio of the reflected voltage V1 minus, okay, appearing at the load side divided by the input voltage or the voltage reaching the load, okay, which is V plus of t minus L by V. So the ratio of reflected to incident must be the ratio gamma L, and for passive loads that we are considering, this will be independent of time, okay. So as long as this ZL is purely resistive, not just passive, it is purely resistive, then gamma L will be a real quantity, and you can actually write down this expression as ZL or equal to RL, is equal to R0 into 1 plus gamma L divided by 1 minus gamma L, and gamma L will also not be complex, it will be real as long as, let me rewrite this, as long as ZL or equivalently RL is real, okay. It could be greater than Z0 or less than Z0, greater than R0 or less than R0, but it has to be real. So which means that only for resistive loads this kind of a reflection coefficient can be developed, okay. So one can actually perform an analysis and obtain the same value for gamma L as we did for the steady state analysis, but provided you have loads which are purely real. Okay, if you have a capacitive or an inductive load or a combination of those loads, this equation will not be true, and you have to perform that in a slightly different way. Alright, so the reason why I went through this set of equations is to convince you that gamma L does not lose its importance when you are analyzing digital waveforms on the transmission line, as long as load as well as the transmission line as well as the source impedances are all real. Okay, so you can similarly define something at the generator side or the source side and call that as gamma G. So of course, what is gamma L? Gamma L is RL minus R0 by RL plus R0, right? And similarly you can define gamma G as Rg minus R0. You imagine that the source impedance now acts like a load, and for the reflected voltages. So here the incident voltage is V1 minus, the reflected voltage would be say V2 plus. Okay, and this ratio would give you gamma G, and that would be equal to Rg minus R0 divided by Rg plus R0. Okay, so this is something that we wanted to write here. Now we have all the tools that is required for us to understand how the wave propagates. So you understand this equation, right? So whatever the source voltage that we have launched, after a certain time delay, that voltage appears at the load. What happens if you are looking at the intermediate point? So you place an oscilloscope between the source and the load on the transmission line. Well, in that case the voltage would start at a slightly earlier time, right? So what time should pass? It would be Z by V, because this V plus of t minus Z by V will be the voltage V plus of t, which is delayed by Z by V. Okay. The way to analyze these transients or these digital step waveforms on the transmission line is to write down what is called as a lattice or bounce diagram. Okay. This is a nice graphical approach. Of course, more complicated analysis has to be carried out numerically, but for this course we will assume that things are simple and we will understand how to use this lattice or bounce diagram. If nothing else, this will at least tell us how to actually approach the problem and obtain some intuitive understanding of the problem itself. Okay. So what is this lattice or bounce diagram? The idea is simple. You have a source side, right? So there is something that is happening along time. So this vertical axis down is the time axis. Okay. Sometimes you find in literature time is normalized with respect to the delay time of the transmission line. You can do that or you don't have to do that one, there is no problem out there. So let us call either this time as absolute time, or one can imagine that there is a time delay normalization, you can do that as well. Now so there is a similar time diagram at the load side as well. So you have a load end and you have a source or the generator end. Load end is characterized by gamma L, generator end or the source side is characterized by gamma G. Okay, and this length would correspond to the length on the transmission line. So with Z equal to 0 over here and Z equal to L corresponds to the load. This is called space-time diagram or lattice diagram, because on the horizontal axis you have the distance between the source and the load on the transmission line, and on the vertical you have the time coordinates. Okay, so you have space as well as time coordinates, therefore this is called as space-time or lattice diagrams. Okay, what happens to that circuit, okay, at t equal to 0 when you switch the source? Okay, so when you switch the source, what happens to the circuit? So there is a step source waveform, okay, and then you have a transmission line connected to the load as well. So this is RL, this is R0. This transmission line has a length L, the propagation velocity is V. Okay, so we have everything that is characterizing this circuit, but what we haven't understood is that if an initial step voltage of amplitude V0 is applied at t equal to 0, what would actually be the voltage on the transmission line? Now, it is very simple to recognize that the moment the switch is closed, RL is not visible to the source, right? The source cannot see RL. What it sees instead is that it will only see the equivalent impedance of the transmission line, and that is nothing but the characteristic impedance of the transmission line R0, right? So this is what this particular step voltage sees just at t equal to 0 after the switch has been closed. Okay, what is the initial voltage? What would be the initial voltage across this one? This initial voltage, let us call this as V1 plus, okay, something that would actually propagate along the transmission line, and this V1 plus from voltage divider analysis is simply R0 by R0 plus RS into the amplitude of the step voltage waveform V0. So this is the voltage that is actually launched on the transmission line, and this amplitude actually begins to travel. Okay. Since these step waveforms can be represented mathematically by unit step waveforms u of t, the voltage V1 plus as a function of time and this one is actually this amplitude V0 into R0 by R0 plus Rs u of t minus Z by V, right. So this is the voltage that is actually being transported from the transmission line from source to the load end. And what we do on this lattice diagram is that we look at this amplitude and then we draw a line which starts at Z equal to 0 and reaches Z equal to L, and we also mark the amplitude here as say V1 plus. This is the amplitude that we have. V1 plus is R0 by R0 plus Rs into V0, okay, and we put an arrow indicating that this movement of this voltage is from source to load. So source actually carries a unit step or a step voltage of amplitude V1 plus on the transmission line. Well, at this point there is a reflection coefficient, therefore this sets up a reflected voltage, right. So this sets up a reflected voltage with an amplitude of gamma L V1 plus. This would be equal to the amplitude of the initial reflected voltage V1 minus, and this would be propagating from load side to the source side. What would be the total voltage at this point? The total voltage will have to be 1 plus gamma L into V1 plus. Why is that so? Because the voltage at any point on the transmission line has to be sum of incident and reflected voltage. Now if you were to put oscilloscope over here and say what is the voltage at this point, you can see that if you put this one halfway through between, then if this distance gives you a time delay of Td, then until Td by 2 there is no voltage, but at Td you will actually see a voltage of V1 plus appearing on the oscilloscope, right. So at the oscilloscope at Z equal to, so at Z equal to L by 2V, which is halfway between, you will see that until Td by 2 you won't see any voltage, then the voltage actually appears.